The Dream Chaser spacecraft is owned and operated by SNC. Although design, manufacturing and assembly is based in Louisville, Colorado, we have assembled a world-class dream team of aerospace companies, NASA centers, universities and international partners, all collaborating to ensure the Dream Chaser is the safest, most reliable spacecraft in the world. We have established cooperative agreements with international space agencies collectively representing almost 24 spacefaring countries with a heritage of success that includes hundreds of missions. For NASA missions, vehicle refurbishment between flights will be performed at Kennedy Space Center in Florida. A typical airplane has large wings that provide the lift to keep the vehicle in the air, while Dream Chaser does have small winglets, or fins, to provide directional stability in flight. The lift is created by the body of the vehicle, the underside, which is wide and flat. Our gentle low re-entry allows us to build thermal protection system (TPS) and an overall vehicle that is reusable with pinpoint landing capability enabled by the lifting body characteristics. The lifting body design gives Dream Chaser a higher lift-to-drag ratio and allows for greater cross-range landing capability, meaning the landing zone at places where it can land is greatly increased. Since Dream Chaser uses all non-toxic consumables, including propellants, there are no environmental or safety hazards that require unique ground support infrastructure. As a result, it has the potential to land anywhere that has a suitable 10,000 feet runway capable of handling a typical large passenger airplane like a Boeing 737 or Airbus 320. Almost immediately after landing, the Dream Chaser spacecraft offers access to cargo and crew. Additionally, a runway landing substantially increases safety and reduces risk because runways are developed, maintained and operated to strict domestic and international standards. With other spacecraft, such as capsules, a distant splashdown into an ocean, a remote landing, crew and cargo retrieval is more labor-intensive, takes longer to complete, requires more support infrastructure and introduces risk including those related to injured crew or sensitive cargo. For scientists, researchers, and medical personnel, the benefits of the near immediate accessibility afforded by runway landings are unmatched. Dream Chaser will experience atmospheric entry with a maximum of only 1.5 gs throughout the flight profile, which is considerably less than existing capsule-based orbital return systems, or even most roller coasters. This attribute makes the Dream Chaser vehicle ideal for sensitive payloads and deconditioned or injured crew members returning from space. Our Dream Chaser spacecraft can be reused 15 or more times, which is more than any other current space vehicle, making the Dream Chaser affordable and responsive. Right now the Dream Chaser spacecraft is designed as a space utility vehicle (SUV) for LEO. The spacecraft is capable of docking or berthing to the ISS and can perform a variety of other missions in LEO including remote sensing, satellite servicing, free-flying, self-contained science and manufacturing, serving as an exploration testbed, or performing active debris removal, cleaning up space trash. The Dream Chaser spacecraft third-generation design builds upon 4 decades of NASA development, i.e., HL-20, and lifting body space shuttle legacy. Dream Chaser is 30 feet and 9 meters long, which is roughly 1/4 the total length of the Space Shuttle orbiters. The Space Shuttle was designed with a spacious cargo bay to allow it to carry large structures to space such as components for the ISS and the Hubble Space Telescope. However, in 2011 ISS construction was completed, therefore, NASA no longer needs such a large cargo vehicle to transport hardware or cargo to and from LEO. Instead, NASA now needs smaller, more efficient transportation systems to transport cargo and crew to and from the ISS. There have been dozens of tests on all major subsystems performed to date, which include extensive thermal heat shield testing, wind tunnel tests, environmental impact tests, system-level tests, flight software analysis, reaction control systems tests and many, many more. A scale, autonomous atmospheric free flight test was conducted at NASA's Armstrong Flight Research Center, Edwards Air Force Base, California in late 2013. With this historic test flight, SNC was able to test and verify the aerodynamic and ground performance of the vehicle. This was the first test conducted on a lifting body spacecraft in over 40 years. Business Area Space Systems.